So this is, let's see here, go back to our intro. Evaluating classes. So, um, debating about how I should about this. Let's see. Okay, so we're going to talk about a little bit of confusion matrix. So this is going to allow us for classification. So this is really useful for any classification besides even logistic regression. So just want to make that clear. So we have this thing. I don't know if we talked. Remind me if we talked about precision versus recall. Does that seem like familiar words that we talked about in the past? I see kind of more confused.
So I know we
Okay.
looked at a diagram very much like this one time, but it was a while ago.
Okay, yeah, no problem. So it's a very similar diagram. I think the one I showed probably was the one from Wikipedia, kind of very similar to this guy. And we have basically, if you imagine this is our full data set here, okay? And then this square is representing, these are the things that we say are true. Like these are our positive ones. The model says these are positive, right? And all the stuff outside of this square are negative, right? And then we can see here in this case, we actually have all the, make sure I have this right, yes. All the filled in squares are actually positive. We should have marked those as positive. And all the ones as little empty squares, those should actually be measured as negatives, right? Those are not true. We shouldn't have caught those in the square. So you can see we made a few mistakes. First of all, we made a mistake that we missed some of the positives. And we also made a mistake of putting some of the negatives within our true model here. So of course we call these ones true positives because we marked them actually as positive and they were in fact positives. And these are true negatives over here. We didn't select them, which means they're negative, and they actually were negative. And of course then that means that some of these ones that should have been positive, we marked them as negative, false negatives. And the ones within this square right here, we actually mark these as false net positives, right? So we said they're positive, but they really shouldn't be. So our accuracy, what that really comes down to is when we say accuracy, what we're saying is how many true positives did we get compared to how many actual positives there are. So I think this is the kind of similar, I've done this before. Let's see if I can draw this out. Is if I drew kind of a square, I could, for example, ideally, I want a model that does like this in orange, where this basically says, okay, these are all the true positives, right? And all the true negatives are out here, and I have no false positives, no false negatives, right? Cool. But this will give us 100% accuracy. We're like, awesome, cool, right? That means like we're good. The problem is if we just measure just accuracy, one way we can draw this rectangle instead, or the square, or whatever you want to call it, is just going like this. Because this then will say, all right, we have all the true positives, or sorry, all the ones that are actually positive, we mark them as true. So cool, that means our accuracy is 100% still. But you can obviously see a problem with this, is that essentially by marking everything as true, we ignore the fact that we are also counting things that are negative as positive. And so accuracy is not good enough essentially to get the nuance of like this classification. So what we do instead is basically pull up something called precision and recall. So precision basically is going to talk about our true positives over all the, what's it called? All like our selected elements, all the ones that we mark positive, which means true positives and false positives. So you can imagine in a good scenario here, so I'm going to draw our little ideal rectangle again so we can reference it, is that ideally we want this guy, right? So our precision then will basically be 100%, right? So you can see we marked all the true positives and we have no false positives. So essentially we have 100%, which would be good, right? But if we had that big, square over here, we would have a whole bunch of false positives, right? Which would mean this would go a lot lower. So it'd be like something like 50%. Recall is kind of similar in the sense that we're talking about more about, in the sense we're kind of looking at how many negatives we get. So we can see we look at true positives over all the things that were actually positive in here. So one of the things that we made false negatives and stuff like this. So in this model, again, we would get 100% because we have essentially no false negatives. But in that very large one where we included everything, right, we would still get, I'm sure I got this right. Yeah, we would still get 100%, but our precision would still be low. So essentially there's this balance between saying you want high recall, high precision, and we balance those two parts. And that's what's going to help us get a better metric than just pure accuracy itself. It takes a little more work in the sense of like trying to figure out what your class is, but it's going to be paid off because now our model is going to be a little more accurate in trying to get those true positives and those true negatives. Okay, does that make sense to you guys? Cool. All right. So just kind of review precision, true positives over all selected positives, right? So that means true positives and false positives. And then recall is going to be our true positives over all positives, which is basically going to be our true positives divided by true positives plus false negatives. Okay. So kind of like high recall, everyone is positive. So we saw like if we choose everything, everything is positive. High precision is like we don't want to make a guess for 100% certain. So maybe only like marking one of them as positive. We get a lot more negatives false negatives, but that doesn't affect our precision. Our precision would still be 100%. So there's kind of a back and forth a little bit going through. Okay, cool. Accuracy, like I mentioned, is basically just our true positives plus true negatives divided by all observations, right? So we're just basically saying, you know, is it marking everything correctly? And it's like, well, that's not the best thing for us to measure. So usually we'll talk about a precision and recall, which gives us to our F1 score. So our F1 score just kind of knows the harmonic mean, and basically it's punishing extreme values. It punishes it if we have a high precision but a low recall, it's not a good F1 score. If we have the opposite where we have high recall but low precision, that's not going to be a good F1 score. So it's a good balance between this two. Note that they treat precision and recall equally. Some cases you might actually say, hey, we really want to encourage, we value precision more or we value recall more. In that case, you can do an F beta score. And basically F beta, basically you put in a different value for beta. So for example, if you put in something like, you know, an F2 score or an F3 score, usually it's F2 or F.05. Basically saying, do you care more about precision or do you care more about recall? Okay, cool. And you can see if I put 1 in here, it simplifies down to the F1 score. But if you're not sure, or if you're just like both are equivalently equal, F1 score is a good metric just to start off as. Okay, cool. Any questions then about how the F1 score kind of represents your recall and precision, and F beta being is a modification of that?
Just a quick question about the formula for F beta. Is the beta squared being multiplied by precision and then recall is added, or is this like a...
This area here?
Or are precision and recall in parentheses being added first?
Yeah, so this part right here, I think the denominator, right?
Yeah.
Yeah, it's just precision being multiplied by beta squared.
Okay, thank you.
Yeah, it's important to do that. It has to be asymmetric, right? Otherwise, if they were symmetric, it would basically like increase both of them. So we're basically saying here is that, for example, if precision is lower, for example, if like precision is like 0.0001, right, times beta squared, some factor in there, we're essentially saying, oh, recall is going to have higher importance, essentially. We're basically saying, well, we're okay if we have precision lower. We're going to boost it up by, you know, some factor. If you had a small beta, for example, a beta that's under 1, right, that would basically increase, or this would decrease precision even further, which means precision is more important in this case.
Okay.
Thanks. Cool. Good question. All right. So, so this is kind of like numerically how we can kind of check this out. So we can actually get a number from like our model, say, what's the F1 score or F beta score? Cool. Confusion matrices allows us to basically look at specifically, well, what things is it messing up on? So this is when we have type 1 errors and type 2 errors, false positives, false negatives. So if you remember that back there, we actually identify which ones are basically off the true positives. So here's a couple from, what's it called? The curriculum. And you can see here, basically, this is the true label, 0 or 1. There's only 2 labels in this case. And then our predicted class. So we can see here, everything on the diagonal here is a true positive. So we identified this as 0, 2 of them as 0, and it turns out 2 of them are actually 0. However, we can see here, we marked these 3 as 1 when they really should have been 0. So you can see here, this is going to be like, if you said 1 is our positive, right? We would say these are false positives, right? Or basically they're just misclassified. This is useful when we talk about like true negatives, true positives. And note that the F1 score only really comes down to the fact that you're using it against a positive or negative, right? But it doesn't make sense if you have multiple classes. And that's where I think confusion matrices make a lot more sense. Because now if we have multiple classes like this guy right here, we can actually see that for 0, 1, 2, 3, we can see how many are actually classified correctly. And then we can see where these are identified differently. And this is actually a really nice way to kind of debug or kind of see where your model does not do a good job identifying. So one example I have is a project I've done with ASL translation. And so this is, so note that this is flipped over from this true label and true predicted label. So this is actually the prediction row right here. And this is the actual, like true labels. And this is actually identifying, if you guys know American Sign Language at all, you can spell out words with your hands, right? So they're called hand shapes. So for example, this is an A, this is a B, this is a C, D, and so on, right? So what I did here, you can see on this diagonal, does a pretty decent job. And I did it percent-wise. So you can see like 82% right here was like identified as A. And you can see kind of going through here, some do better than others. So some letters are identified more easily. But you'll notice, like, for example, this A right here, this was the true label. And we can see that sometimes, in this case, it was labeled as T. Well, if you know about sign language, it's like, okay, like this is the letter A, and this is using images to detect whether it's an A or a B, right? So you can see it was an A, 82%, pretty accurate, right? Sometimes identified as C, right? So you can see a very small percent, but this right here is T. So the letter T, this is A, this is the letter T. And you can see like, oh, that looks very similar. That makes sense that they would make this mistake. You can kind of see something similar here where, let's see if I can find a quick one. Q is a really bad example, but M's another one too. So you can see M right here sometimes get misidentified as N, which is this column right here. So M is this letter and this is N. So you can quickly see, oh, this is where it's making these mistakes. And what's kind of nice about this too is that this is one type of model right here. We can actually use another confusion matrix. So like we have a new model. So this is a different model that performs differently on here. And we can see where this model fails. And you can see here as well is that in this case, is that actually? Okay, yeah, you can see it still messes up on A and T, but there might be other parts where it doesn't do as well. For example, we see K and V, which I think, let's see if this works here. K and V is relatively small, 15%, and this is about 17%. So this is like K and this is V. So you can kind of see, depending on the angle, what's going on here. So you can kind of identify parts that are like you need to have your model focus more on. And they're nice to compare models of like, where does it mess up? Here, I think I found a good one right here. So this is E, and this is O. So in this model, this is the letter E, which is what it actually identified, and this is the letter O. So maybe, you know, something it misidentified well, right? So 11%. But you can see here, I think it was a much lower percent. It does a, this one right here actually does a pretty good job identifying O. Like if it's actually an O, it's a good job of not making it an E instead. So you can see the difference between these different models where this one's more likely to classify an E as an O versus this one's never going to really do that, at least not as frequently as the other one. Okay, so that's a really useful way to compare multiple models at once, and you can see multiple classes. Cool. Any questions on these confusion matrices? Okay, cool. I always suggest, I think the curriculum kind of shows like, you know, how to do a confusion matrix. I sometimes see them, you know, when people do their, do their confusion matrix, they'll use numbers and they'll just put the numbers out, but no coloring. I would suggest highly doing the coloring because it does help you really emphasize, like, you know, you can look at these numbers, but it's really quickly easy to identify when you have the different colors spectrum going through here. Okay, cool. So that is our evaluation metrics. Any questions on this for between F1 score, confusion matrices, any of those parts? Sound pretty good? Okay. So our last part, we have about 15 minutes. So I think this might go pretty good, well. So our ROC curve and AUC. So our ROC curve, so I think both of you guys have gone through this part of the curriculum, right? Just getting the idea of here. This is where, let's see here. I might not finish all of this, and I want to make sure I take the time to go through it. So if we don't get to like all of it, we'll continue it on for next time. But I kind of want to go through parts of this. So before I even talk about what the ROC curve is, I'm going to go back to, like, if you remember back with our logistic regression. So let's see this site. I'm going to do some drawings. So I mentioned before is that when we had our drawing of logistic regression, right? We have this logistic regression going like this. Okay. And that's kind of like, you know, the model says, oh, that's for logistic regression, right? And then what it is, we'll say like, this is like our true, like this is our true and this is our negative, right? Which is basically equivalent to 1 and label 0. Okay, so let's say, for example, we have heart disease. Let's say, this is gonna be a little, let's say if you have heart disease, right? So a bad heart, that's gonna be true. So this test is saying, can you identify a bad heart, right? Heart disease. And then this one right here, for example, was like a good heart, right? So a happy heart. So that's 0, meaning that there was no heart disease detected, right? And then let's say on this metric, obviously we can say multiple dimensions, but we're going to stick to like, just our target in one feature. Let's say, for example, this is like weight, okay? So you can probably imagine weight has some factor in whether you have heart disease or not, and identifying someone has heart disease, although it's probably not the only metric. You can imagine there might be someone who's a higher weight. For example, if you are taller, like you're going to have a higher weight, but not necessarily have heart disease, right? Or other factors too, like if you're a smoker or whatnot, different things. So we can have these different data points, and let's see if I can draw this in black. So imagine we have different weight points, and I'll just draw it on here before we draw it up here. So we say, okay, we have some weights who are relatively small, and then we have some higher weights over here, but most people are kind of like average. Okay, so these are kind of like our distribution of weights. And then what happens, we basically put it through our logistic regression, right? So this is kind of like our prediction, right? Saying, okay, like go ahead and make the prediction off of these points. I don't know if X is the best thing, but like these are not X's, these are just data points, right? So you imagine it's like, okay, in our predicted it says, okay, this Y right here, these actual labels are going to be like X, let's say this person does have heart disease. This one doesn't have heart disease. This one does. This person doesn't. This person doesn't. This person has heart disease, but this person doesn't. Okay, so you can see here, like it's basically, these are the true labels themselves. And this logistic curve right here is describing how well this actually fits, or saying what the prediction is. So like, for example, I'm gonna label it in red. We'll do it that way. This one right here will be labeled right here. This guy will label right here. This one will be labeled right here. This one will be labeled right here. This one will be labeled right here. This one will be like right here. Hope I can kind of see that a little bit. This one's going to be right here. If I had a good grid system, that would be a lot easier to see. This will be right here. So the thing is that it's like, okay, based on here, we can basically get a value between 0 and 1. And essentially what we'd want to do even is say, okay, who has heart disease and who doesn't? And so this is where we do create basically like a threshold. So if you imagine if I have some kind of line like this, I can say, okay, if I have this line like this, let's see if I can move things around. No, I cannot. Okay. So you can see like, okay, everyone above this line has heart disease. So if your value is, let's say this is 0.04 or something like that, if your value is above 0.04, that means you have heart disease. Or yeah, you have heart disease. But you can imagine that some of these points, so you can see like this one right here, these two, would actually end up being labeled incorrectly. And the way you can kind of visually see this is that if I drew a line right where it intercepts, see if I can do that. If I draw it like right here, everyone to the left of this line does not have heart disease, and everyone to the right of this does have heart disease, at least based on my prediction. And so this is how you can basically say this threshold. So if I move this threshold now, I'm going to draw it with zoom because I can kind of draw on top of it and get rid of it. If I instead have a threshold that's like up here, it's like, okay, you have to have with a certain percent, like let's say 0.9, and then we say you have heart disease. Then we draw a label right here, right? We can say everyone to the right, left of this, well, these people do not have heart disease. And everyone to the right over here does have heart disease. And this is kind of how we can essentially say, okay, this is where based on our threshold, this this horizontal line is our threshold, and we can adjust that up and down kind of going through. And that will essentially, as we move that line up and down, that's going to move the line on the weight axis of saying, who does have heart disease. So imagine if we have like, for example, way low over here, say, okay, you have to have, if you have a value like 0.1, that means you have heart disease. And can you see we're going to have a lot more, in this case, false positives. Like these people do not have heart disease, but they're going to be identified as they have, right? Versus something that's a little bit higher for me. Oh, I'm using two different drawing tools. You can see this line right here where the threshold is very, very high. It's like, okay, we only say you have heart disease if you're above like 0.9 or 0.95. Then you're going to see, okay, we're going to have a lot more false negatives where we're going to misidentify these people over here as not having heart disease when in fact they do. So you can see here that basically the false negatives and false positives are going to be dependent on what our threshold is. So that's what our ROC curve is going to represent, is that we're going to basically make our logistic line and going to adjust that threshold up and down kind of deal And that's going to determine, you know, how many false positives or false negatives we have. Note that there is no perfect answer here, right? There's no way I can draw this threshold where we'll perfectly get everyone as, at least on just weight, I correctly identify everyone. So we'll always have some false positives or false negatives, and we have to decide, you know, what are we willing to accept? Okay, does that make sense to you guys, this visualization? Just thinking like how we use that threshold. Cool. So keep that in mind as we kind of go into our ROC curve. So evaluation curves, there we go. So our receiver operating characteristic curve, which no one ever says, it's always called ROC curve. I've never heard anyone ever say this. If I saw, I actually had to look this up because I couldn't remember what this was. But what's our worst kind of classifier? So if our worst kind of classifier really is just guessing, note that our worst classifier is not the same thing as someone who's picking the opposite. So if you say the true label is 1, but you choose 0, and if it's 0, you choose 1, that's actually a really good classifier in a lot of ways, because essentially you're just doing the opposite. The way I kind of think about this is like, if you have like that friend who's like very different from you, you know, but you're friends and everything like that, and they hate all the movies you love, and they love all the movies you hate, then you can always ask them like, hey, did you like that movie? You know, a movie you haven't seen. It's like, did you like that movie? It's like, oh, I loved it. Then you know not to watch that movie. And if they say, oh, I hated that movie, oh, it's probably a good movie. So in a lot of ways, they're a good classifier. So that's kind of like our worst one really is just randomly guessing. Okay. So evaluating our model. So this is when we're just going to look at just the logistic regression. This is where I just went through a little bit. What is this guy? Oh, that's when we literally drawing. That's why we just did. So we can kind of draw this out as kind of like saying these different classifiers. So this is coming from the curriculum. And so you can imagine this like red and this green saying like, you know, how many people are identified as our true positives versus our true negatives. And you can see there's might be a classification kind of crossing over. So we don't want a lot of crossover, right? As we kind of saw on our kind of Zeitboard over here, if I drew this over here and there's a lot of crossover where there's a lot of people in between here that can be identified true and positive, it's going to be hard to make a model on that. So just kind of looking at this part, and this is where that decision boundary, so that's our threshold that we talked about here, that is representing essentially how many false negatives and false positives. This is essentially us moving that threshold, in this case along horizontal, well, I guess along the x-axis, versus here, we're kind of looking at drawing on the y-axis, but that's the same value going on here. And this is just identifying how many true positives and how many true negatives we have. Okay, so I think the best one though is actually, where is this? Okay, this is our ROC curve. So yeah, I'll talk about this and I'll show you guys the example online. This curve right here is representing one model. And essentially each point on this curve is representing where we draw that threshold. So you can imagine starting here, our threshold starts at 0. And as we move our threshold up in this diagram here, this is going to tell us how many true positives and how many false positives we have down here. So this is our true positive rate. Basically, as we move it up and up and up and up, right, our true positive rate is going to get higher and higher and higher, right? We're going to identify more most until we get all the way to the top where we draw our bar at the very top here. If we do that, then we're going to have a true positive rate of 1, right? Because we're going to include everyone. But as we draw that up, we're also saying how many false negatives we have. If we draw it all the way up, we're going to include some false negatives in there. So our false negative rate is going to be increased. So ideally what we want is right here. We want up in this basically true positive rate, but it's 1, and false positive rate is 0. Note that most models, you just will never be able to do that, right? Based on our logistic curve. But without looking at the threshold, we can actually say how well is our model performing. And this one right here, for example, is like our worthless model, kind of joking here, is that essentially this is random. It's like, well, there's really no way to tell. Like as we move the threshold up, it doesn't really change anything. Basically, it's like it could either be false or it can either be negative or positive. So that's not a really great model. Note that usually our ROC curve won't go the other direction. You notice that basically it'll stay above this curve. And that's because underneath this curve is essentially is that best friend who's like the opposite of you, where like you can just ask them the opposite. So it turns out with gradient descent and a lot of, if you optimize these things, you usually won't go into this territory because essentially it's like, oh, well, if that's true, if it's negative, like it's the opposite of you, you just do the negative side and you flip it over. So it'll tend to always be on this side. But essentially what this is showing is that this green line is a better model than this blue line here. Okay, and there's depending on the threshold, you probably want a threshold that would be right here, which would give us kind of like the best balance between the two. But note that depending if you care about precision or recall, you might be okay over here or over here. Okay, does that make sense to you guys? Okay, I know I have a few minutes left, and so I won't go into this part. I do want to show a little, where is it? I'll go over this next time too, that way take time. Oh, where is it? I had an example of showing this and I realized maybe I got rid of it. Okay, I'll show it to you guys next time then. I just realized, oh, it's this guy. Duh. Okay, so let's just go to here. And I'll leave you guys with this kind of like graph, and then we'll kind of talk about this, is that if we change our model in our, if we change our model right here, this is our different model going through here, there's some crossover, and we can imagine dragging this threshold. This is our threshold going through, and you can see that red dot there on the top left is describing our different, this one model, which is the distribution of these two distributions, okay? And this is basically just saying, okay, like this is where the threshold's drawn. And so you can imagine if our model basically has a very model that's very close together, you're never going to have a really great ROC curve. And so our threshold can identify, for example, a lot of, let's say true negatives. But as we go over here, right, might have more true positive rate. But if we go into the middle here, we're always going to have some crossover. So the best model is really going to be something that can separate this out the best. And you can see this ROC curve kind of adjust here. Okay, cool. So we'll talk more about this next time for sure. And we'll go a little bit closer and we'll show you a little bit more of this coding example of how you draw a ROC curve and how that looks like when our example with the iris data. All right, cool. So I'll go ahead and stop it here, unless you have got some quick questions. Okay. Yeah.